Okay, let's talk about matrices. A matrix is just a rectangular grid of numbers arranged in rows and columns. Think of it like a spreadsheet. Each cell holds a number, and the whole thing is wrapped in square brackets. For example, if you have a matrix with 2 rows and 3 columns, like this, 2, -1, 0 on the first row, and 3, 4, 5 on the second row, we call that a 2 by 3 matrix. The size is always written as rows by columns. Each entry is labeled by its row and column position. So the entry in row 2, column 1, would be 3. But matrices aren't just tables of numbers, they're tools. They help us represent systems of equations, transform geometric shapes, store data, and perform calculations efficiently. Imagine trying to solve 100 equations with 100 unknowns. Matrices let you organize that chaos and solve it systematically. Now, matrices often work hand in hand with vectors. A vector is just a list of numbers, usually written as a column. For example, 5 on top of 6 is a two-dimensional column vector. If you multiply a 2 by 2 matrix by that vector, you get a new vector. Let's say the matrix is 1, 2 on the first row, and 3, 4 on the second. Multiply that by the vector 5, 6. You take the dot product of each row with the vector. So row 1, 1 times 5 plus 2 times 6 equals 17. Row 2, 3 times 5 plus 4 times 6 equals 39. So the result is the vector 17, 39. The matrix has transformed the original vector into a new one. That brings us to matrix multiplication. If you have a matrix A with size m by p and a matrix B with size p by n, then their product, AB, is an m by n matrix. The entry in row I, column J of the product is the sum over K of AIK times BKJ. This rule is designed to match two key ideas. First, composition of transformations. If B transforms a vector and A transforms the result, then AB represents doing B first, then A. Second, solving systems of equations. If you write a system like x plus 2y equals 17 and 3x plus 4y equals 39, that's the same as the matrix equation A times x equals B. Now let's talk about operations. You can add matrices of the same size by adding each corresponding entry. You can multiply a matrix by a scalar. Just multiply every entry by that number. The transpose of a matrix flips its rows and columns. The identity matrix is like the number 1 for matrices. It doesn't change anything when you multiply by it. And the inverse of a matrix, when it exists, is the matrix that undoes its effect. If A times A inverse equals the identity, then A inverse times B gives you the solution to AX equals B. Geometrically, matrices are machines that perform linear transformations. In 2 dimensions, a matrix can scale, rotate, or shear a shape. For example, a scaling matrix with S and T on the diagonal stretches the X and Y directions. A rotation matrix uses cosine and sine to rotate a vector around the origin. A shear matrix slants shapes sideways. That's why matrices are everywhere in graphics, physics, and robotics. There are also special types of matrices. Square matrices have the same number of rows and columns. Diagonal matrices only have non-zero entries on the diagonal. Zero matrices are all zeros. Symmetric matrices are equal to their transpose. Orthogonal matrices preserve angles and lengths. Sparse matrices are mostly zeros, great for saving memory. Low-rank matrices compress information and show up in data science. Now for some deeper ideas. The determinant of a square matrix tells you if it's invertible and how it scales area or volume. The rank tells you how many independent directions the matrix spans. Eigenvectors are special vectors that don't change direction when transformed by the matrix. Their corresponding eigenvalues tell you how much they're stretched or shrunk. These concepts show up in everything from stability analysis to principal component analysis. So, where do we use matrices? Everywhere. In science and engineering, they solve systems of equations. In computer graphics, they rotate and scale objects. In data science, data sets are matrices. Rows are observations, columns are features. In machine learning, neural networks are built from layers of matrix operations. In physics, matrices describe forces, vibrations, and quantum states. In networks, adjacency matrices represent connections. In economics, matrices model inputs and outputs. In cryptography, they encode and decode messages. Computationally, matrices are handled by tools like Python's NumPy, MATLAB, and R. These platforms let you perform matrix operations efficiently, and modern hardware like GPUs is optimized for fast math, which powers everything from AI to simulations. So, to sum up, a matrix is a structured way to store data, a tool to transform vectors, and a compact way to solve many equations at once. They're used in almost every technical field because so many real-world systems are linear, or can be approximated that way. If you want to go deeper, try solving a system like AX equals B by hand, or visualize how a matrix rotates a shape in 2 dimensions. Once you start seeing matrices as transformations, not just tables, the whole subject opens up.